Okay, I'll start the session. Am I audible to everyone? Can someone confirm? Okay. Is there anyone who did not attend yesterday? Is there anyone for whom this is the first session? Okay. Yesterday I covered topics from week 2. Today I'll be doing topics from week 1 because last Friday I did not take a class. This is a compensatory class for week 1. Okay. So if you are not interested in listening to week 1 topics, then there will be two more live sessions tomorrow by other TAs that will be on topics covered in week 2. Am I clear? Okay. I hope everyone has. Okay, since you are here for the first time, I'll tell you about myself. I am Sachin Sampath. I'll type out the full name in the message box. I did my BTech in NIT Surathkal in the ECE department. I did my MTech in IISc. That was also in the ECE department. My MTech was on communication and networks. Now I am doing my PhD in IISc under Dr. Balaji Sundarajan in the field of cache-aided communication and other applications of caching, mostly private information retrieval and coded caching. Uh, okay, that's about myself. I'll go ahead and start with this session. I'll be solving 15 questions from previous year assignments. This was done in 2022, and many of the questions will be similar to the questions that you have in your assignment this semester. So, this will be helpful in solving. If there are any doubts, you can unmute yourself and ask. No need to hesitate. Okay, first question. They have given a binary number 101010. We have to convert it to decimal. Uh, do you guys want to try yourself? I'll give you 1 minute. Try it yourself and type the answer in the chat. What it? Okay. Okay. Many people are saying it is B42. Let's see. Uh, when you are given a decimal number, suppose you are given the number 567. What does that mean? This means that you have 5 hundreds, 6 tens, and 7 ones. So this is the hundreds, tens, and units place. So this number represents 500 plus 60 plus 7. The same way for this binary number, you will have place values for each position. So when you write the number 101010, This position has a value 1 or a weight of 1. This is the units place. This is the 2's place. This is the 4's place. And you keep multiplying this by 2. So this will be 8, this will be 16, this will be 32. So you can simply multiply and write it out similar to the decimal number. You will get 32 into 1 plus 16 into 0 is 0 plus 8 into 1 plus 4 into 0 is again 0 plus 2 into 1 plus 1 into 0 is 0. So this will be 32 plus 8 plus 2, which will be 42. That is option B. Okay. Question number 2. They have given a decimal number 76 and you have to write the equivalent hexadecimal number. Try it out. There is no doubt in the first question, right? If you have any doubts, you can unmute yourself and ask. Four C. Students are answering as 4C. Okay, let's check it out. The method you have to follow to convert from decimal to any base is you keep successively dividing by that base. So hexadecimal system has base 16. So you have to divide 76 by 16 and keep the remainder to the side. 16 4 times is 64. Remainder is 12. And 16 0 times is 0. Remainder is 4. And 12 in hexadecimal will be A is 10, B is 11, C is 12. So this will be C. And you have to write the number in this order. So the number will be 4C. That is option D. Okay, you are able to use the method to solve the question, but do you know why we are doing this? Why are you dividing by 16? How is it giving you the correct answer? Can someone tell me? Why did you divide by 16? You okay? But why is this algorithm that they have given giving you the correct representation? How does it work exactly? Hmm. Yeah. So, in a sense, Let's take the decimal number I had taken earlier, 567. This side written as 500 plus 60 plus 7. So when you divide this number by 10, what remainder will you get? Both 500 and 60 are multiples of 10. So they won't leave you any remainder. So 7 is not divisible by 10. So you will get 7 as your remainder. Right? And then you take the remaining part that has been divided by 10. That will be 56. Right? 500 plus 60 divided by 10 will be 56. Again, when you divide by 10, you can write this 56 as 50 plus 6 divided by 10. So here this 50 is a multiple of 10. So it won't give you any remainder. 6 is not divisible by 10, so the remainder will give you 6. So by successively dividing by 10, you can get the units place, tens place, hundreds place as you go on dividing. Same thing will happen with 16. That's kind of the logic behind using this algorithm. It's very simple to follow the algorithm, but you also need to understand why you are doing this. Okay. Question number 3. They have given a decimal number 45 base 10. You have to write the binary equivalent of it. This is similar to the previous question, except that there you have to divide by 16 because it's a decimal to hexadecimal. Here it is decimal to binary. Why don't you try and tell me the answer in the chat box. One zero one one zero one. What option is that? It's C. Okay. Anyone else? A. Omkar. Try again, Omkar. You have to use the same method as in question number 2, except that you have to divide by 2. Well, let me show the steps. 45 is the decimal number. You want to convert it into a binary. So you divide by 2. 222 times is 44. 1 will be the remainder. 211 times is 22, remainder is 0. 5 times is 10, remainder is 1. 2 times are 4, remainder is 1. 2 ones are 2, so remainder is 0. Into 0 times remainder will be 1. And you have to write the answer in the opposite order. So binary equivalent of 45 decimal number will be 101101. Yeah, that is option C, like Shravya and Vijay Kumar have typed out. Omkar, did you understand or is there any question? Because you had typed out A. Did you understand how we got C? Okay. If you have doubts, you can unmute yourself and ask me. Okay, question number 4. They have given you an octal number and then you have to write the decimal equivalent. No, hexadecimal equivalent. Because from the options, they are given all the options are in base 16. So from base 8 to base 16, you have to convert. Try to solve it. A. Okay. What method did you use, Vijay Kumar? How did you do it? Okay, you converted to binary and then you converted to octal. Okay, that is the easiest method to do it. You could convert this octal number to decimal and then convert it back to hexadecimal, but that will be uh, a lengthy process. So it's easier to do the follow the method that Vijay Kumar has used. Gurudas, yes, you will get the recorded video. I will upload it on YouTube. Yesterday's session and today's session, week 1 and week 2, both I'll upload. And yesterday's session, there was some problem with the video. The screen is not, the slides are not clearly visible in yesterday's session. But the notes will also be sent to you guys. You will be given a link to the notes. So if you have the notes with you, then you can just watch the video. Channel, even the YouTube link will be told to you. The nptel coordinator should tell you. I have not uploaded yet. After I upload, they will let you know, I think. If they don't let you know, then you ask me next week. I will make sure to tell them. Okay. Other people have also solved. Omkar is saying A. Vijay Kumar also said A. Fine. For others who have not solved it yet, I will solve it myself. 651 124 base 8. To convert it to binary number, you simply write the binary equivalent of all the digits. So 1 is 001. You write it in 3-bit format. 5 is 101, 6 is 110, and 1 is 001, 2 is 010, 4 is 100. Now this is the binary number. To convert it to base 16 hexadecimal, you have to group 4 bits together. So these 4 bits, and then you have this singular 1, but it's okay. Before this one, you can add as many zeros as you want. So you can write this one as 0001. So that will be 4 digits. And when you are going to convert digits to the right of the decimal point, you should start from the left and go to right. So this will be one group, and this will be another group. And this 0, it's just 0. Even if you add zeros, nothing will change. You can take away this 0 also. So this will be 1. 1010 is 10, which will be A in hexadecimal. 1001 is 9. 0.0010 is 2. And 1010 is again 10, which is A. So this will be in base 16. Okay, any doubts here in question 4? Seems like there are no doubts, so I'll move on to the next question. Convert binary to octal. This is a simple question. You can do it quickly and tell me the answer. To convert from binary to octal, if there is no decimal point, you simply start from the right and group 3 bits together. So let me write down the number 110 110 001 010, and you group these 3 bits and these 3 and these 3. This will be 2. This is 1. This is 6. This is 6. So it is 6612 in octal. Okay, you're doing this grouping. Do you know why this works? Have you written it down and try to understand what is actually happening? Can someone explain? Why are you grouping 3 bits together? How does it give you the correct answer? Animesh, do you know? What do you mean by why is it only 3 bits? Hmm. 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 Yeah. And I can write down what is actually happening, the mathematics here, and show it to you. So this 110 the previous question I had told you that you can think of this as having place values. So this place value will be 1. This is 2, 4, 8, 16, 32, 64, 128. Or let me write it in powers of 2. This has value 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7, 8, 9, 10, 11. So when you write the expansion of this number, it will be 2 power 11 into 1 plus 2 power 10 into 1 plus 2 power 9 into 1, no, into 0 plus 2 power 8 into 1 plus 2 power 7 into 1 plus 2 power 6 into 0 plus 2 power 5 into 0 plus 2 power 4 into 0 plus 2 cube into 1 plus 2 square into 0 plus 2 power 1 into 1 plus 2 power 0 into 0. Now take out 2 power 9 from these three numbers. 2 power 9 into 2 square into 1 plus 2 power 1 into 1 plus 2 power 0 into 0. Now here you take out 2 power 6 in the next three numbers. That will be 2 square into 1 plus 2 into 1 plus 2 power 0 into 0. And the next three numbers, take out 2 cube. 2 square into 0 plus 2 power 1 into 0 plus 2 power 0 into 1. And here you take out 2 power 0. So you will get 2 square into 0 plus 2 power 1 into 1 plus 2 power 0 into 0. This 2 power 9 you can write it as 2 power 9 2 cube whole cube. So it is actually 8 cube. And 2 power 6 will be 2 cube whole square. So it is 8 square. This is 2 cube 8 or 8 power 1. And 2 power 0 same as 1, same as 8 power 0. Thus this turns out to be 8 cube into what is this? 4 plus 2, 6 plus 8 square into this is 4 plus 2, 6 plus 8 power 1 into this is 1 plus 8 power 0 into 2. So you can see this is like an octal number. If you write an octal number 6 is 1 2, then it will have place values 8 power 0, 8 power 1, 8 square and 8 cube. That's the same thing that's given here. So it is 6612 to the base 8. That's how the mathematics works out. You can do the same thing when you are grouping 4 bits for a hexadecimal, when you convert to hexadecimal also. If you write out the expansion of the binary number and then you keep taking powers of 16 outside, so you'll get groupings like this, but there you'll have to group every 4 bits. Question number 6. Vijay Kumar says it's D. What do you guys think? What about other people? You have two n-bit binary numbers and you're adding them. How many bits will you need maximum to represent the sum of those two numbers? Can you do it with n bits? Or do you need n plus 1, n plus 2? Well, we are taking the sum. The sum will have a maximum value when each of the addends will have maximum value. So, for an n-bit number, the maximum value of an n-bit number, what is it? It's 2 power n minus 1. Correct. Because you start from 0 and go to 2 power n minus 1. For example, n is equal to 4. You have 4 bits. You start from 0 0 0 0, go up to 1 1 1 1. This is 15, which is equal to 2 power 4 minus 1. And this is the maximum value an n-bit number can have, 2 power n minus 1. If you add two such numbers, then their value will be 2 power n minus 1 plus 2 power n minus 1, which is 2 times 2 power n minus 1, which is 2 power n plus 1 minus 2. Next, what is the maximum value an n plus bit number can have? An n plus 1 bit number can represent. So with n plus 1 bits, you can go up to 2 power n plus 1 minus 1. If you observe this number, let me call it a, and this number, let me call it b, a is equal to b minus 1. So a is less than b. So this number 2 power n plus 1 minus 2, this can be represented using only n plus 1 bits. So the answer is n plus 1. Option D. What is it, Vijay Kumar? This is clear to everybody? Okay, I'll go to the next question. Find the sum of the following negative numbers represented in sign plus magnitude 5-bit register using 1's complement. So the two numbers are minus 1010 and minus 0101. In what is the 1's complement of 1010? It is 0101. And what is the 1's complement of 0101? That is 1010. You add them, you will get 1111. And since it's a negative number, answer is minus 1111. Correct. Any clarification needed in this question? Hmm. Hmm. No, see, the number they have given is minus 1010. That's not one's complement form, right? The numbers are represented in the register using sign plus magnitude notation. Then we have to do the sum add using one's complement. Ah. Answer should be in sign plus magnitude form. Hmm. Let me think. Um let's at least think whether it is the right answer. So minus 1010 is minus 10, right? Minus 0101 is minus 5. And when you add them, you'll get minus 15, which is minus 1111. Correct. So the answer is correct. But mhm. It only works out because these numbers are just the opposite of each other. Uh, yeah, what you said is right. Doesn't feel like it's the proper method. Okay, we'll come back to this question at the end of the session. After I go through the remaining questions, then we'll sit down and find out what went wrong. For now, I'll move on. Is that okay, Animesh? Yeah, we'll complete the other questions, and then only those students who are interested in figuring this out can stay, and the rest of the students can leave. Okay, I'll. We have to do question 7. We have to revisit that. Okay, question number 8. I think a similar type of question is given in your assignment this time also. 110 to the base x is equal to 132 to the base 4. Then what is x? How do we do this? So whatever the base is, powers of the base will be the weights. So x power 0, x power 1, x square. This will be the give you the place value of the digits, like hundreds, tens, units in the decimal numbers. This 0 is weighted by x power 0, 1 is weighted by x power 1, and the other one is weighted by x square. And this is equal to 132 base 4, it's 4 power 0, 4 power 1, and 4 square. That means x square plus x plus 0 is equal to 16 plus 4 3s are 12 plus 2, which is 30. X square plus x is equal to 30. You can write this as x into x plus 1 is 30. And you can write this as 5 into 5 plus 1. So x is equal to 5 is correct. So it's option B. Well, this equation has only one positive solution. You can try to solve the quadratic equation also. You can write this as x square plus x minus 30 is equal to 0. The other solution is minus 6. You can try that out yourself. Minus 6 square is 36. 36 minus 6 minus 30 is 0. But the base of a number system cannot be negative. So we have to take only x is equal to 5 as our solution. That is option B. Question number 9. They have given a binary number, we have to find the decimal equivalent. This is, we simply need to expand this out. Here there are fractions, so there are digits after the decimal point, but it doesn't change anything. Previously you had given weights as 2 power 0, 2 power 1, 2 square, and when you move to the right of the decimal point you will get negative exponent in the weights. So this is weighted as 2 power minus 1 or half. This is 2 power minus 2 or quarter. 2 power minus 3, 1/8. So it is 4 times 1 plus 2 times 0 plus 1 times 1 plus 1 times half is 0 times 1/4 plus 1 times 1/8. 4 plus 0 plus 1 is 5. Half is 0.5, 1/8 will be 0.125. So it is 5.625 in base 10. So option C. Tell me. 11010, yes. And the other number will be no, but uh, minus 5 11010, right? One's complement. Hmm. Yeah. Yeah. Okay. Okay. Well, but I'm not sure that's how the register will do the computation. That's the same thing that we did earlier. We just didn't write out the sign bit. That's all. Ah, okay. 1 0 0 0 0 will be 1 1 1 1. Is what you're saying. Okay. That is, if you write it like that, then that is fine. But we don't know how the computer would do addition, right? Why does it keep the sign bit the same and only flip the other bits? Ah, ah, but will the computer do that? Is this how the computer does it? Is this how it's supposed to do? Okay. Hmm. Okay. If that's how it is, then okay. I didn't know that. Thank you for telling me. Yeah. So we'll correct this right now. So you write this as 1 1 0 1 0 and 1 0 1 0 1. And when you do one's one's complement, you write this. You keep the sign bit the same, but you write it as 0 1 0 1, and this becomes 1 0 1 0. And then you add. You'll get 1 1 1 1 0 with 1. Since 1 is carried, you'll add that here. So this will be 0 0 0 0 with 1. Since this is 1, you take the 1's complement, you'll get 1 1 1 1. Is that right? Okay. So it is minus 1 1 1 1. Okay. Well, for MCQs, it will work out either way. You can simply do minus 10, minus 5 is minus 15 and write the answer. But if there are subjective questions, then you will have to do what Animesh said. Animesh and who was the other person? He also Upendra Patel. Okay, thank you guys. Since that is clarified, we'll move on to the next question. This one is over, right? Any doubts in? Well, there are probably no doubts in ninth question. You'll go to question 10. 7526 in octal minus y, that is also in base 8, is 4364 in base 8. where xn stands for x to base n. You have to find y. Try solving it. Well, you can simply shift the y to the right side, and you can then write this as y to the base 8 is equal to 7526 base 8 minus 4364 base 8. Okay, it is 7526 minus 4364. 6 minus 4 is 2. 2 minus 6 you can't do that, so you borrow 12 minus 6 is 6. 4 minus 3 is 1. 7 minus 4 is 3. It's 3162 base 8. Is that right? Is that correct? Why is it not correct? Ah, hmm. Why is that? Yeah, so, yeah, yeah, yeah. So, this thing is wrong. So, 7526 minus 4364. 6 minus 4 is 2, that is okay. But when you are carrying over a digit, you are actually carrying over 8 to here. So, it is 8 plus 10, 2, 10 minus 6, which is 4. And then 4 minus 3 is 1, 7 minus 4 is 3. So, this you need to be careful. It's not that complicated, but when you are borrowing, what are you actually doing? So let's ignore the first digit. Let's take 526364 and let's take in base 10. If you want to subtract this, 6 minus 4 is 2. Okay. When you borrow, what exactly are you doing? You have this hundreds, tens, units, 5 hundreds. You are taking away 100. So you are left with 4 hundreds. And you are giving that 100 to the tens place. So 100 is how many tens? It is 10 tens. So you're actually giving 10 tens to this 2 tens. So in total you have 12 tens, and you are subtracting 6 tens from that. So you're left with 6 tens, and you have 4 minus 3 100s. So similarly here also, if you are doing in base 8, this is 1's 8's 64's place. So 6 minus 4 is still 2, but what is this 5? It is 5 64's. You are taking away 164 and giving it to the 8's place. So this will become 4 64's. 164 is 8 8's. So to the 8's place you are giving 8 8's. So you are actually giving 8 to this digit 2. So 8 plus 2 is 10. When you subtract, you will get 4. 4 minus 3 is 164's. And that's how it works. It's not too complicated, but you have to keep that in mind. They have given 3162 purposefully so that people get confused and mark that as the correct answer, but it is actually 3142. It is option C. Okay, question number 11. So you have to convert to base 4. The principle is the same as all the other bases, base 2, base 8, base 16, whatever base is given. For the digits to the left of the decimal point, you divide by 4 and keep the remainders. And you write the remainders in one particular order. And for the digits to the right of the decimal point, you keep multiplying by the base. And whenever you get some digit to the left of the decimal point after multiplying, you take that out and write it. So what I mean to say is, take away this 225 divided by the base 4. So this will be uh, 56 times remainder 1, 4 14 times is 56, remainder 0, 4 threes are 12, remainder 2, 4 zeros are 0, remainder 3. So it is 3201. So from this 3201 itself, you can see that the correct answer is option B, because the other parts are different in the different other options. For the decimal part, it is 0.4375. Vijay Kumar, your mic is on. You have to mute your mic. Vijay Kumar, can you mute your mic? I'll see. I'll try to. Okay, I can't mute your mic. No, fine. So for the decimal place, you multiply by 4. You multiply this by 4. 4 5 is 20, 2 carried, 4 7 is 28, plus 2 is 30, 3 is carried, 4 3 is 12, plus 3 15, 1 carried, 4 4 is 16, 1.75. You take this one and write after the decimal point. Then you take the remaining part, 0.75. Again you multiply it. 4 5 is 20, 2 carried, 4 7 is 28, plus 2 30, 3 carried, 3.00. You get 3, you write it here. Then what you're left with is just 0.00, and when you reach 0 you can stop. Some numbers you won't reach 0 no matter how much you multiply. Then you can write a few digits, however much accuracy you want, you can write up to there and then stop. So the correct answer is option B. Question number 12. What is the ones complement of 01101? How about you type the option in the chat? It's very easy. Everybody can do. Vijay Kumar, your mic is on. Okay, Vijay Kumar has said that the answer is C. Did no one else try? Tell me. Ah, hmm. 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 Yes. Well, they're asking you to do one's complement, so it's you just flip the bits. That's all. They're not asking you the ones complement representation of this number 01101. If they'd asked you what is the representation of this particular number in one's complement system, then what you said is right. That it is the number itself, because positive numbers, their one's complement representation is simply the binary representation. But that's not what they've asked, right? They've asked you to do the one's complement operation. So doing the one's complement is the function that I had given in the lecture PDF. If you have a number x, one's complement can be thought of as a function f of x, where f of x is equal to 2 power n minus 1 minus x. So in that way, if you think of one's complement as a function, you will have to subtract this number from 11111, right? Yeah, but like you said, if they had asked what is the representation of this number in one's complement number system or one's complement representation, then it would have been 01101. So one's complement, flip the bits. That is f of x is 2 power n minus 1 minus x, which is 11111 minus 01101 10010. Option C. 8-bit 2's complement form of minus 45 base 10. So here they are asking what you said earlier. You have to write the 2's complement form of this number. 2's complement form of 45 is what? Um, 1, 2, 4, 8, 16, 32. So 32, 40, 45. But it's 8 bits, so this only has 6 bits. You have to add 2 zeros. 0, 0, 1, 0, 1, 1, 0, 1. That is 45 base 10. Yeah. One's complement of this is 11010010. One's complement. And two's complement is add 1 to one's complement. So 11010011. It's option B. Okay. Addition of hexadecimal numbers DEF.12 base 16 and 12EF.C base 16. Answer is also in hexadecimal. So you can directly carry this out in hexadecimal itself. Let's write out the alphabet values first. A is 10, B is 11, C is 12, D is Gauri Shankar R. Yes, I'll send this whatever I'm writing down. I'll make a PDF and then upload it on Google Drive, and then I'll send the link to nptel, the coordinators. The coordinators will then share the link with you. Even the video will also be uploaded. It will be uploaded on YouTube. The link for both of them will be sent, but I won't be sending it directly. I'll send it to nptel coordinators. They will send it to you. You don't have to call me sir. All of you can just call me Sachin. I am just a first year PhD student. Okay, D is 13, E is 14, F is 15. Let's do the addition. It's the same thing that you do in decimal, except that you have other symbols. D, E, F, 1, 2, and 1, 2, E, F. Let's see. After decimal place, after the last digit, you can add as many zeros as you want. So I'll write this as 0. Here, before the decimal point, to the left, I can add as many zeros as I want. So I'll write that also as a 0, just for convenience. Now we just add 2 plus 0 is 2. C plus 1. What is C plus 1? C is 12. 12 plus 1 is 13, which will be D. D2. If you are answering in the exam, you can see this D2 and directly say that only option B has D2. So if they have given multiple choice, you can easily mark the answer as B and move on to the next question. But I will do the remaining addition anyway, just for your understanding. F plus F is 15 plus 15, 30. What is 30 in hexadecimal? Well, if you can't get it off the top of your head, you can divide by 16. So ones are, and remainder is 14. 16 is 0, the remainder is 1. 14 is E. So it is 1E in hexadecimal. So F plus F is 1E. You write down the E and carry over the 1. Then again you do this. E plus E will be 14 plus 14, 28. Plus the carry 1 is 29. 29 again divided by 16. If you take it one time, you will get a remainder 13. 0 times remainder 1. 13 is D. So this is 1D. 1D, you write down the D, carry the 1 over. D is 13 plus 1, 14 plus 2, 16. 16 is 1, 0. Because the hexadecimal, the place values will be 16 square, 16 power 1, 16 power 0. So if you write a 1 and 0, it will be 16. 1, 0, you write down the 0, carry over the 1, 1 plus 1 is 2. So it checks out. 20DE dot D2. Answer is option B. Question number 15. 16-bit 2's complement representation, the decimal number minus 28 will be 28. First you write down the positive 28 in binary form. It will be 0, 0, 0, 0. First few bits will all be 0, and then 28, 16 plus 8, 24 plus 4, 28. So this will be the 16-bit representation of plus 28. To do 2's complement, first you do 1's complement. All the bits, all the bits are flipped, and then add 1. So this will be option C. Okay. Well, those are all the questions that I have to solve, but I still have quite a lot of time. Is there anything you want to ask me? Any questions? Otherwise, then let's see. I'll try to find questions from a different year. I have not written the exam, nptel exam, so I can't tell you if that will be enough. You should ask the regular TAs in the discussion forum. No, today do regular TAs also take questions? Who was the TA? No, no, he is also a temporary TA only. I mean, external TA, you could say. He's also from PMRF side. Yes. The regular TAs, I don't know whether they are taking live classes. They are probably only setting the question paper and other logistics. So you should ask in the discussion forum. The mailing list kind of thing is there, right? There's an option to ask a question. There you should go and ask. Hmm? Okay. So then I'll try to find some more assignment questions. I had access to some other questions also. I have to find them. Hmm. This is still 2022. Oh, these questions might be repeated. Yeah, you have this question in your assignment, right? Oh, okay. So 2019 assignment, they have repeated questions, so I can't solve those. Thought I had access to 2020 questions also. I'll see. Oh, somebody was asking about textbook. I am not sure. Other people are suggesting Morris Mano. Yeah. So Morris Mano should be enough. Well, there are no restrictions in these sessions. These are not compulsory sessions. So, if you want to leave, you can leave anytime. You can leave even in between sessions when questions are being discussed. This is only for your help. So, if you have other important work, you don't need to force yourself to come here. But it's best if you join early and at least for the first 1 hour, if you stay, a lot of questions can be solved, and this will help you solve your own assignments because many of the questions are similar, right? So you can just copy the method. Is anyone still there? Do you want me to solve some more questions? Morris Mano, which edition? I don't know. I don't know which edition. I took this course 6 years ago, so now I don't know which edition everyone is following. You want me to solve questions from week 1 or week 2? Week 2, okay. I'll. I don't have a PDF or anything as such for any more questions, but I searched on YouTube and someone seems to have uploaded the assignments for the year 2020. So, as long as there are no common questions with your current assignment, I'll solve those questions. Is that okay? Additional questions. Give me 1 minute, okay? I'll find the questions. I'll check if there is no overlap with your assignment. Okay. The first question is IEEE single precision floating point representation of minus 0.75 base 10. Would you like to try on your own or should I just explain? I also not solved these questions, so I'll solve it with you. If there are any mistakes that I make, you can correct me. So, how do we do this? It's a negative number. So, the first sign bit is 1 because it's a negative number. Then you consider 0.75 base 10, just 0.5 plus 0.25. 0.5 is 0.1 base 2. This 0.25 is 0.01 base 2. This number is 0.11 base 2. So for IEEE representation, you need to have 1 to the left of the decimal point. So you can write this number as 1.1 base 2 into 2 power minus 1, because we are shifting the decimal point to the right side. So the exponent is minus 1 and significand is 0.1. We imply this one, the 1 is implied in IEEE single precision format. So you don't need to write the 1. You don't need to store the 1. You can store only the remaining part after the decimal point. And you need to add a bias of 127 to the exponent. So 127 plus minus 1 is 126. And in IEEE, this exponent is represented using 8 bits. So in 8 bits, what will this be? 1, 2, 4, 8, 16, 32, 64, 128. 126, we don't need 128, we should start for 64 plus 32 is 96 plus 16 is 112 plus 8 is 120, 124, 126. So that will be your exponent. So the floating point representation is, first you write the sign bit, which is 1 because it's a negative number. Then you write the exponent 0, 1, 1, 1, 1, 1, 0. Then you write the remaining part after the decimal point here, which is 1. And you need to write 23 digits here, because overall this whole thing should have 32 digits. This is 1 digit and this is 8 digits, so you need to write 23 digits. So the remaining digits you fill it up with zeros. So this is the FP representation of the number minus 0.75 base 10. Okay. From what I am seeing, many questions are repeated from previous year assignments also. So you can try to find previous year questions and solve them all, and you'll get better idea of how to solve. Next question. The minimized form of a plus ab plus abc plus abcd plus AB, C, D, E plus etc. is. So this you can take A common and write it as A into 1 plus B plus BC plus BCD plus BCD etc. should be equal to A times 1, because 1 plus anything, any literal, any variable will be 1. So you can write it as A times 1 and you will get A. Himanshi, which question do you want me to explain? This previous one? This one? Okay, you have seen the lecture video, right? On converting a decimal number to floating point number. I'll explain the procedure. So a decimal number, you can easily write it on a paper. 0.75 base 10, it's okay. But for a computer, it's difficult. Computers can store only ones and zeros. They can't store this directly as 0.75. And the thing is, suppose you have one bit. A bit can be 0 or 1. Right? So you can only store two values with a single bit. What about 2 bits? You can store 4 different values, 0001, 1011. So you can store 4, that is 2 square numbers using 2 bits. Similarly, using n bits, you can store 2 power n different numbers. But there is another much cleverer way to represent more numbers using the same n bits, and that is this floating point representation method. So suppose you have some number 12.5, you could write this as 1.25 into 10 power 1, right? Then what you do, you store this exponent, the power of 10 to which you are multiplying, and you store this part only, 25. And you say that whenever you write 25, you actually mean 1.25. So whoever sees this will understand this number to be 1.25 into 10 power 1. Here there is not much difference. You had to store 3 digits. Here also there is 1 and 2, 5, 3 digits again. But when you are doing in binary representation, when you are storing binary numbers and when you are storing large numbers, you can go up to a much higher number by using this type of representation, where you are storing the exponent and the mantissa separately. So how you do that is, first you take this number minus 0.75. I'll explain it here. Minus 0.75. First we need to represent in binary, so convert it into binary number. The way you convert a decimal to binary is by multiplying by 2. You take this 0.75, you multiply it by 2, you will get 1.5. And then you write 0. If you get a 1 here, you write that down. 1. Then you remove this 1, take only 0.5 and multiply it by 2. You will get 1.0. You take this one and write it next. Then you remove that 0, you will get 0.0. When you get 0.0, you stop this process. So this 0.75 in base 10 is nothing but 0.11 in base 2. Or another way to do it is 0.75 is 0.5 plus 0.25, which is equal to half plus 1/4. And in binary system, after decimal point, the place value is whatever comes here must be multiplied by half, whatever comes here must be multiplied by 1/4. So if you write 1 1, that means you are multiplying 1 by half and adding 1 multiplied by 1/4. So 0.75 base 10 is 0.11 in binary. That's the first step. You convert the decimal number to binary. So 0.75 base 10 is 0.11 in binary. Now, similar to how I had done 12.5 is equal to 1.25 into 10, you write this number 0.11 base 2 also. You write it as if you shift this decimal point to the right and write this as 1.11, then you have to multiply it by 2 power minus 1. Here instead of 10 you are multiplying by powers of 2. Suppose you had shifted the decimal point one place to the left, then this would have been 0.011 into 2 power 1. So since you shifted it to the right, it's 2 power minus 1. Now what you do is, since it's minus 0.75, you represent this minus with 1 bit. If this the first bit, you have 32 bits with you. Okay, this is stored inside the computer. First bit is the sign bit. If you store it as 0, then it means that you're storing a positive number. If you store a 1, that means whatever number next you are storing here, that's a negative number. So here in minus 0.75, you're storing 1. Next, you store this exponent. The exponent is minus 1. But what you do is you add 127 to this exponent and then you store the binary form of that. When you add 127, you get 126 in binary format. Previous lectures you had actually taught how to convert to binary. So you convert this 126 into binary form and you get 01111110. You write this after the sign bit. So 01111110. Next, you take only this part. 1.1, you ignore this one because that is implied in IEEE standard. Whatever you write here, you have to put a 1, put a decimal point, and then write this number down. So you ignore the 1, you have 0.1. 0.1 is nothing but you can add as many zeros to the right side as you want. It doesn't change the value of this number. So you write whatever is here in this block. 1 0 0. You keep going on. This should be 23 bits. So it keeps going on until 0. That's why at the end you get this as your floating point representation: 1 0 1 1 1 1 1 1 0 and 1 0 0 0. Did you understand, Himanshi? Okay. Does anyone else have any doubts? Otherwise, I'll end the session.